And we're back. Before the break, we were talking about the implications proof of coherence has for security.
This is a major selling point in the paper. The security guarantees stem directly from these quantum mechanical principles, not from math problems that might be breakable later, especially by quantum computers.
So how does that stop common attacks, like, say, double spending?
Okay, double spending. The defense there is primarily the no-cloning theorem and wave function collapse. Physics says you cannot perfectly copy the unique quantum state embedded in that valid signature sigma.
Can't copy it perfectly.
Right. And if you try to use it, the measurement aspect collapses the state. So the idea is you physically can't duplicate a valid signature to authorize spending the same asset twice. It's prevented by the physics.
Okay, physically impossible to duplicate. What about forged signatures? Someone trying to fake one.
If someone tries to create a fake sigma that looks like it came from a valid quantum experiment, the paper argues it would inevitably fail the coherence check. Trying to fake that specific type of quantum entanglement would, well, break the entanglement properties. The validation function f, checking against that Beeman threshold, would spot the discrepancy. It wouldn't look quantum enough.
The physics check catches the forgery attempt. Makes sense.
I can see you're trying to beat it, like in your head. You're trying to figure out how you can work around it.
Yeah, I totally am. There may not be a way, though. At least I don't see it. It's wild to think about, though. Something truly unbreakable. What about things like 51% attacks?
They become irrelevant, according to the paper, because validation is this local physics-based check. An attacker controlling 51% or even 99% of the nodes can't force an invalid block onto the chain. Each honest node independently verifies the block against the physical rules embedded in sigma. An invalid sigma fails the check, regardless of how many nodes claim it's valid.
Node consensus doesn't override the physics check.
Precisely. Node count is decoupled from block validity. And similarly for Sybil attacks creating lots of fake identities. The paper states node identity plays no role in the validation. It's all about whether the sigma in the block header passes the physics test. It doesn't matter who presents the block.
Okay, so the core validation seems resistant. What about forks? Or someone trying to replay an old transaction?
Address 2. If you change anything in a block, alter the transactions, which changes the Merkle root, you need a new valid sigma for that modified header. Generating a new valid quantum sigma without access to the original quantum foundation setup is described as effectively impossible.
Right, you can't just compute one.
Exactly. And if you try to just reuse an old valid sigma on a new block or at a different position in the chain, the paper says that would either create a header hash collision, making it obviously invalid, or violate a rule against duplicate sigmas being used, causing the local validation function to reject it.
So it seems like the physics provides built-in resistance to many classic attack vectors. Okay, shifting gears a bit. If this system offers such inherent security and instant validation, where could you actually use it? What kinds of real-world applications does the white paper envision?
Oh, the list of potential applications is huge. It covers a really broad spectrum, largely because of those core properties, unforgeability and instant physics-backed finality.
Give me some examples.
Okay, financial services is a big one. Think quantum-secure transactions with immediate absolute settlement. Asset tokenization where the token itself is physically impossible to counterfeit. Cross-border payments settling instantly without relying on chains of intermediaries.
Unforgeable digital assets.
Oh.
Yeah, that would be massive.
Definitely. Then there's supply chain management. Imagine quantum-verified provenance. You track a product's origin not just with a database entry, but with a record tied to something physically unforgeable. Fighting counterfeit goods, ensuring ethical sourcing, that could be revolutionized.
Knowing for sure where something came from, provably, that's powerful.
It really is. Healthcare applications, too. Secure patient records, tamper-proof by physics, verifying clinical trial data integrity, tracking pharmaceuticals to prevent fakes. Imagine a medical history guaranteed correct by quantum mechanics.
That changes trust in health data entirely. What about government or public sector?
Things like voting systems, unforgeable, maybe anonymous, vote records that are instantly verifiable, immutable land registries, transparent public records. A voting system inherently resistant to many forms of digital tampering seems, well, incredibly relevant.
Hugely relevant. I saw Internet of Things mentioned too.
Yeah, quantum-verified device identity. With billions of connected devices, knowing a device's claimed identity is physically authentic seems crucial for security. It tackles a fundamental trust issue in IoT.
And identity generally.
Right, identity and access management.
Mhm.
Things like self-sovereign identity, where your credentials have this physics-based verification behind them.
And the last one was intellectual property.
Yeah, things like unforgeable timestamping for when a creation was made, managing licenses, distributing royalties automatically based on usage tracked on this secure ledger. Think about proving undeniably when you invented something or wrote a piece of music.
That's a big deal for creators. Looking at that whole list, I mean, which ones jump out to you as potentially the most impactful?
That's tough. Personally, the supply chain provenance and the identity government applications feel very compelling. The idea that a digital record, who owns what, who voted, where medicine came from, who you are, could be physically impossible to tamper with. It just cuts through so much of the uncertainty and fraud we deal with now.
I agree. Those feel really fundamental, but we have to take a quick break. But when we come back, we'll look beyond the theory. Can PoCoh be implemented? Right after this.